Hello, today we're going to do a review of power series because eventually, as in at the very end of this section, we are going to use power series to solve differential equations. So a quick review is in order as well as an introduction to a few new topics. Um, let's just see how this works. All right, power series. Power series are nothing more than polynomials. That's it. It's just a sum of polynomial terms. But the idea is that they could be centered about 0 or centered about some other value, 2, 7, 13, -3, whatever. We call it A, okay? And so we have these two different forms. Centered about x equals A, we would see the summation symbol, this funny looking Greek letter, and it would be summing up C sub n times x minus A, all raised to the n power. Now that summation symbol, the Greek letter sigma, below it says n equals 0 and above it says infinity. That is the counter. It counts. That's all that it does. It starts at n equals 0, and when you write out what that term is, that would be c sub 0 times x minus a to the 0, which is just c naught, and then the counter moves on to n equals 1, and that gives you c1 times x minus a to the 1. And then the counter moves to 2, and we get c sub 2 x minus a all squared. And it goes on like this forever. Okay, and so you get an infinite number of power functions where the powers are increasing by 1 at each step. Now, if we choose to center about x equals 0, it just simplifies the look of everything. And so we still have the sigma notation, but now instead of x minus a, we just have x to the n. And so when our counter starts at n equals 0, we get c naught x to the 0, which is just c naught. When n is 1, we have c1x. When n is 2, we get c2x squared. And this goes on forever and ever. We're going to focus on those series, the ones centered about x equals 0. And we'll use those later in order to solve differential equations. But in the meantime, we have to talk about a special series, and then we need to review all of our convergence techniques and all of those things. So one example of a power series that we saw before was the geometric series. That was a one where you have a plus a times r plus a times r squared and so on and so forth. And it all adds up to a, the sigma notation, where n goes from 1 to k, of a times r to the n minus 1. And when we learned this in Calculus 2, we learned that this summation, if k goes to infinity, then this will go to a over 1 minus r, so long as r is between -1 and 1. Now, if k is finite, we can get a representation of the sigma notation with this a times 1 minus r to the k all over 1 minus r. And that's not what we're really interested in. It's just that is a representation of the sigma notation. We are more interested in the a over 1 minus r when k is infinity and when r is less than 1 in absolute values. Okay, so I'm going to erase that. So in our geometric series, we get convergence if r in magnitude is smaller than 1. So that's just values of our, we get -1 to 1 for r. If r is equal to 1, that's no good. And if r is bigger than 1 or smaller than -1, that's no good. So that's the case where we would get divergence if the absolute value of r is greater than or equal to 1. But in a geometric series, all the terms have the same coefficient a. And for our purposes, we need to be able to work with a power series that has different coefficients for each term. But they are still just coefficients. And coefficients are not affected by the value of x. Okay? So that it ends up being okay that we have different coefficients for every term. Now, because we will be solving differential equations using power series, we have to be able to determine a domain of definition, which is also known as the interval of convergence for our series solutions. And to do this, we're going to have to use the absolute ratio test to determine the interval, And then we'll need any one or two of the other series convergence tests to test the endpoints of the intervals. So we need to review these processes. So the steps for finding the interval of convergence of a power series, where the series is n equals 0 to infinity of c sub n x to the n, we would use the absolute ratio test. We let a sub n and a sub n plus 1 be consecutive members of the series. And then we look at the limit as n goes to infinity of the absolute value of the ratio of a sub n plus 1 over a sub n. And if that limit is some value L that's less than 1, we get convergence. If it's a value of that is equal to L that's equal to 1, that is inconclusive. It gives us no information. And if we get a value greater than 1, we have divergence. And in the case of inconclusive, we have to use another test. Okay? The radius of convergence is called big R, and this we'll be able to determine this from the inequality that's found in the first part. And the interval of convergence, we're going to test the endpoints of the interval that's found in the first step for convergence. I'll go over an example in just a little bit, and we'll really get a review of that. So this is more of a generic example, but let's just see how to run through this with some general steps when we're dealing with y equals the summation, n goes from 0 to infinity, of c sub n times x minus a to the n. Well, in that particular series, I've written out for us that a sub n is c sub n times x minus a all to the n. And a sub n plus 1 is c sub n plus 1 times x minus a to the n plus 1. So I'm going to use the absolute ratio test on that and look at the absolute value of the ratio and take the limit. So I start with my generic form. The limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. This is equal to the limit as n goes to infinity of c sub n plus 1 times x minus a to the n plus 1, all over c sub n times x minus a to the n. Well, n of the x minus a's in the denominator cross out with n of the x minus a's in the numerator. And so we're only left with an x minus a. The c sub n plus 1 over the c sub n, those could be positive or negative, okay? And probably positive, but we'll leave them in absolute values for now because we don't know. But the x minus a is completely independent of n, and so that can come out in front of the limit so long as you keep the absolute value symbols with it. Do not lose your absolute value bars. The minute you lose them, what you're saying doesn't make any sense anymore. We have to, use the language of mathematics and the proper notation of it. But now let's say that the limit on that ratio of c sub n plus 1 over c sub n is equal to some value L. Okay? So we get a value L. This is the result of the absolute ratio test. L times the absolute value of x minus a. Now, we can force convergence by creating an inequality. We take that L times the absolute value of x minus a, and we say this needs to be less than 1. This is forcing convergence right here. And then if we isolate the absolute value of x minus a, this gives us that the absolute value of x minus a is less than 1 over L, where we can let R equal the 1 over L. Remember, R is the radius of convergence. So this right here is the radius of convergence. You don't need to memorize this because it'll be a number that you get, not a letter, okay? And then if we solve the absolute value inequality, remember that if we start with an absolute value is less than some number R, the interpretation of the absolute value being less than something is a compound inequality. Minus R is less than x minus a is less than R. You better drop those absolute value bars once you make that change, okay? So then we solve the complex inequality or compound inequality by adding a to both sides. And so then we get x trapped between two numbers, a minus r and a plus r, whatever they happen to be, where big R is the radius of convergence, and the interval of convergence is the interval that has endpoints a minus r and a plus r. But those endpoints must be tested for convergence in the original series using a series convergence test. So let's just take a look at some of the common tests that come up when we test the endpoints. The first most common one to always remember, but most likely gets forgotten most easily, is the divergence test. This doesn't tell us anything about convergence, but it does tell us about divergence, which is important too. So if the limit of a sub n, the series or the sequence that's inside the series, is not equal to 0, then the series is divergent and you're done. That's why it's good, right? So we're not like trying to do more work. If we know right away it's divergent, then we do not include that endpoint. But let's say that the divergence test is inconclusive. So if the limit is equal to 0, that doesn't actually tell us anything. The series may or may not be convergent at that point. We need to check another test. So the harmonic series is a common series that shows up. If we get the sum of 1 over x, we know that's a divergent series, and so we would not include the endpoint. If we notice that we have 1 over x to some power, x to the p, that will converge if p is greater than 1, but it'll diverge if p is less than or equal to 1. And I should say that our series will have n's in them, not x's, but please just know that the letter that's used is not what's important. The alternating series will come up. That's a sum of, you get an alternator in there, a -1 to the n, times some a sub n. That series converges if the following two things hold. Number one, a sub n is bigger than a sub n plus 1. In other words, future terms in the series get smaller. And the limit of a sub n as n goes to infinity is 0. Okay, so those two both have to hold. If the limit is not equal to 0, then that's already telling you divergence by the divergence test. Okay. Now then there's the comparison test, which doesn't show up quite as much, but we want to just review it. So this is when we compare to a known convergent or divergent series. So for example, if I had a series where it was 3x cubed minus 10x squared plus 15x minus 1, all over 5x to the 4th minus 3x squared plus 1, and that would be where x was the counter, then I would need to, gosh, this is terrible because I have x's and my counter should be x's then as well. Okay, so then what I would compare to is the highest degree term in the top over the highest degree term in the bottom, and that would be my comparison test. So if I look at 3x cubed over 5x to the 4th, that simplifies to be 3 over 5x. And then that 3 over 5 can come out in front, and then we're looking at a multiple of the divergent harmonic series. And so that comparison test can be really nice when you just focus on the ratio of the two highest degree terms in the numerator and the denominator. All right, let's look at an example. Find the interval of convergence of the series that starts at 1 and goes to infinity of x minus 2 to the n, all over 3 to the n times n. Okay, so in this one, I need to look at the ratio test, the absolute ratio test. And what that says is we want the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Notice that our terms are fractions. And so when I write this out, I'm going to look at the limit as n goes to infinity of the absolute value of a sub n plus 1 times, and then I'm going to flip my, I'm going to look at 1 over a sub n. Okay, so a sub n plus 1 would be x minus 2 to the n plus 1 all over 3 to the n plus 1 times n plus 1. That's all a sub n plus 1 times, if I divide by a sub n, that's the same as multiplying by 1 over a sub n. So I would just reciprocate it. So now the numerator is 3 to the n times n. The denominator is x minus 2 to the n. Okay, now I can start simplifying things. I notice that in the x minus 2's, there are n of them in the bottom that cancel out with n of them on top and leave 1 on top. With the 3's, there are n of them on top and n plus 1 in the bottom. So n of the 3's divide out, and I'm left with 1 3 in the bottom. The n over the n plus 1 doesn't simplify. Let's rewrite this. This is equal to the limit as n goes to infinity of the absolute value of x minus 2 over 3 times n over n plus 1. Okay, the x minus 2 over 3, I can pull that out in front so long as I keep absolute value bars over it, because that x could be negative. So this is equal to the absolute value of x minus 2. The 3 is positive no matter what, so I'll keep that out of the absolute values. And then times the limit as n goes to infinity of n over n plus 1. Technically, n over n plus 1 I know is a positive number, but I'll just keep those absolute value bars done until I've evaluated the limit. The limit on that fraction is 1 because the degree of the top is equal to the degree of the bottom. And so I get a final answer of the absolute value of x minus 2 over 3 times 1. And if you forget what you have to do here, you kind of get stuck. We have to force convergence. And to do that, we say that the absolute value of x minus 2 over 3 has to be less than 1. That's forcing convergence. And then we have something to solve. Multiply both sides by 3. We get the absolute value of x minus 2 is less than 3. This right here tells me that my radius of convergence is r equals 3. And then I need to split this up into a compound inequality. So we're going to solve. So I get minus 3 is less than x minus 2 is less than 3. Add 2 to both sides. I get negative 1 is less than x is less than 5. And so this tells me that my interval of convergence is the interval from negative 1 to 5. But we're not done. We have to test the endpoints. We don't know if we can include negative 1 or include 5 or neither or both. So we got to test the endpoints in the original series, which again was the series n goes from 1 to infinity of x minus 2 to the n over 3 to the n times n. Okay, so first I'll check x equals negative 1 by plugging it into the series. So I get the sum, n goes from 1 to infinity, of negative 1 minus 2 to the n over 3 to the n, n. This is going to be the sum, n goes from 1 to infinity. On top I get a negative 3 to the n. And negative 3 to the n is like a negative 1 times 3, all raised to the n power. All over 3 to the n times n. And so now I can clearly see, like, we got to remember our properties of exponents. If I have a product in those parentheses, that nth power applies to both. So this becomes the sum, n goes from 1 to infinity of negative 1 to the n, 3 to the n, over 3 to the n times n. And finally, we get the sum, n goes from 1 to infinity of negative 1 to the n over n, because the 3 to the n's divide out. This is an alternating series. So I'm going to use the alternating series test. Okay, let's see. Is a sub n, the first question is a sub n bigger than a sub n plus 1? Well, let's look at an example. If n is 3, I have 1/3 is greater than 1/4. Yes, that's true. And we could continue on to 1/5, 1/6, 1/7, and so on and so forth. So it is a decreasing sequence. That's the point of that. But then number 2 says, is the limit as n goes to infinity of 1 over n, not with the alternator, just with the sequence, 1 over n. Negative 1 to the n is an alternator. It's not part of the sequence. It's part of the series. So the limit of that is 0. And so we could say we have convergence. It converges at x equals negative 1 because it passes the alternating series test. Okay, next check is x equals 5. When we plug in 5, we get the sum. N goes from 1 to infinity of, in parentheses, 5 minus 2 to the n over 3 to the n times n. That 5 minus 2 to the n is a 3 to the n in disguise, so that's going to simplify with the denominator. We get the series, as n goes from 1 to infinity, of 1 over n, which is a divergent harmonic series. So then we could say that the interval of convergence, also known in our case as the domain, is including -1 all the way up to 5, but not including 5. Okay, that's it. So that kind of reviews the absolute ratio test, and then the alternating series test, and then just a comparison with a divergent harmonic series. Okay. Next topic is shifting indices. You see this just a little bit in Calc 2, but depending on, which class you took, you may not have seen it. So we got to talk about this. How can we shift the indices so that a series will start at n equals 5 and go to n equals 10, and the sum will still be the same? So I have this series, n equals 0 and goes up to 5 of n. And so if I was to write that out, when n equals 0, I get 0. When n is 1, I get 1. N is 2, I get 2. N is 3, I get 3. And so on to n is 5, I get 5. And when I add those all together, I get 15. Now, if I was just to shift the indices, say n goes from 5 to 10 of n, I would get a different value. That would be 5 plus 6 plus 7 plus 8 plus 9 plus 10, and that does not equal 15. So it's not okay for us to just shift in the counter. We have to offset shifting in the counter. And the way we do it is if we add in the counter, then we're going to subtract in the sequence. And so down below I showed that. We've added in the counter. Now instead of starting at 0, we start at 5. Instead of ending at 5, we end at 10. But then notice in the sequence, there's a subtraction. So now it's n minus 5. As long as you do the opposite to 1 as what you did unto the other, you should be good. And so now if I plug in 5, 6, 7, 8, 9, and 10 into my sequence or my series and add them all up, it's the same as adding up 0 plus 1 plus 2 plus 3 plus 4 plus 5, and we get 15 again. So these two series, although they look different, they are the same. But one was shifted for convenience. And so here's my golden rule for shifting indices. If you add to the counter, subtract in the series. If you subtract in the counter, then add in the series. And you can read these backwards. If you add in the series, subtract in the counter. If you subtract in the series, add in the counter. And it works. Your book does something different. They do a substitution. For some reason, that substitution always messed with my brain until one day somebody showed me this, and this is what I've used since then. And so this is how I teach it because it helps. All right, next topic is adding series with different indices. So in these two series, I have the sum, n goes from 1 to infinity, 2 times n plus 2 times c sub n times x to the n minus 1, plus the sum where n goes from 0, not 1, but 0 to infinity, 6n c sub n x to the n plus 1. There are two problems with these two series, and the two problems are the reason why I cannot add it. Number one, the powers of x are not the same. Remember when we add powers, like when we add polynomials, we have to add like with like, so x squared goes with x squared. That means we can't combine x to the n minus 1 with x to the n plus 1. Those are different. The other issue, one of them starts at 1, one of them starts at 0. These are bad problems, but they're fixable. So the first one we need to fix is the powers of x, and you do need to go in this order. If you go in the other order, you're going to undo the work you did. So we always fix the powers of x first, and they must be the same so that we can combine like terms. Okay, so we have same powers. So it looks like if we were to fix the powers of x, in the first series, since it's x to the n minus 1, I'd like it to be x to the n, which would mean I would need to add 1 to all the n's that are in the sequence and subtract 1 from the counter. And in the second series, I have x to the n plus 1, and I need that to be x to the n. So I'm going to subtract 1 from all the n's in the sequence and add 1 to the counter. And that should work. Once we've fixed everything, the indices will not be the same. One of them will start at 1, one of them will start at 0, and we need the counters to start at the same place if we're going to add them together. So to handle these issues, we're first going to fix the powers of x. They should both have a power of n. It's always n, not n minus 1, not n plus 1, it's n, okay? If you decide to be different, you're going to confuse the whole process for solving differential equations later. So there's a reason for consistency in mathematics. It's so that the processes that we give you work, all right? So we need things to be x to the n. So for the first series, we are going to add to the series and subtract from the counter. And what that looks like is I get the sum, subtracting from the counter by 1, we get n equals 0 to infinity. In the sequence, I have 2 times, now I'm going to add 1 to the series, okay? So where it's n plus 2, I'm going to add a 1, and it becomes n plus 3. Then I have c sub n, and the c sub n, that n also needs to have a 1 added to it. And then the x to the n minus 1, I'm going to add a 1, and it will simplify down to x to the n. Okay? The second series, it looks like we need to subtract from the series and add to the counter. All right, so if we add to the counter, we get the sum, n goes from 1 to infinity, of 6. Now that n, we need to subtract from there. Okay, so it'll become in parentheses n minus 1. The n with the c, that becomes c sub n minus 1. The x to the n plus 1, we're going to subtract that 1 and be left with x to the n. Okay, so that looks pretty good. That is not finished though, because now, although we have the n's, the power for x, we do not have the same starting point for our series. So we have to fix that, okay? To make them start at the same place, we must add out the n equals 0 term in the first series. And if we add out that 0th term, then the counter can start at 1. So here's what that looks like. Okay, so I'm going to have my sum. Sorry, I'm going to add out my 0th term. And my 0th term is 2 times, let's see, if I plug in 0 for n, I get 0 plus 3. And then I have c sub 0 plus 1. And then I have x to the 0. That's the 0th term. Plus, now the series, this is still the first series, it can start at 1 now and go to infinity. So I rewrite it, 2 times n plus 3, c sub n plus 1, x to the n. That's just the 0th term. And then the series written is the first term. Let's write term. First terms and up. Okay? Plus the second series, which already started at 1 and goes to infinity. And what's in it is 6 times n minus 1, c sub n minus 1, x to the n. Okay, so now they start at the same place. They have the same powers. Let's combine them. I gave way too much room for this. Okay, so what we're going to do right here, I can simplify things just a little bit. This 0th term, it simplifies to be 6 c sub 1, x to the 0 is just 0. And then I can go ahead and pull out a sum. n equals 1 to infinity because it's the same counter for both. And inside, I have a 2 times n plus 3 c sub n plus 1 x to the n plus a 6 times n minus 1 c sub n minus 1 x to the n. But it's not fully added together until I factor out that x to the n, since it's common to both. And so what I'm going to be able to do then is see like a general form for all my coefficients when I do that. So when I add them all together, I have 6c1 plus the sum, n goes from 1 to infinity, of 2 times n plus 3 c sub n plus 1 plus 6 times n minus 1 c sub n minus 1, close the parentheses, all times x to the n. So now I could let the counter run. I could start it at n equals 1, and I could figure out what the coefficient is for x to the 1. At n equals 2, I could find the coefficient for x squared. At n equals 3, I could find the coefficient for x cubed, and so on and so forth. It's an ugly coefficient with the way it's written right now, but plugging in n values, I get nice numbers. Of course, they would be in terms of the c's. So we got to see what we'll do with those later. Okay, but that's it for adding them. And you'll have homework where you have to shift the indices and change the powers of x in order to get your series added together. Okay. Before we can use power series to solve differential equations, we need to talk about differentiating a power series. It's not very hard. It amounts to nothing more than differentiating a polynomial, which is nice. So if our power series is y of x equals the summation of c sub n x to the n, if I write out what that is, it's just c naught plus c1x plus c2x squared plus c3x cubed plus c4x to the fourth, and so on and so forth. If I differentiate this term by term, y prime of x, it's just taking d dx of that form that I have written out above, the c naught plus c1x and so on and so forth. Now notice if we distribute the d dx through, the c naught goes to 0. c1x becomes c1. c2x squared becomes 2c2x. c3x cubed becomes 3c3x squared, and so on and so forth. Okay? And so in general, because we see that 0th term goes away, like that constant goes away, our counter is now starting at n equals 1. So we start the counter of the derivative series at n equals 1. And a similar situation is going to occur if we find a second derivative, which we will in the next section. Not this one, but in 6.2. And so if we find a second derivative, then the counter is going to start at n equals 2, and so on and so forth. So in general, here are the forms for taking the derivative. If we take the derivative, I want to show this kind of in long form, y prime of x equals, we can bring the d dx inside the summation, and the c sub n is just a constant, and we can just focus on d dx of x to the n. And so the sum, you're not taking the derivative of the summation sign, you're not taking the derivative of the c sub n's, you're taking the derivative on the x to the n's, which would be nx to the n minus 1, and we see that right here. If we were to take a second derivative of that, then the n minus 1 would come down and be a multiplier as well. Okay, so it follows the power rule that we learned for power functions way back in Calculus 1. Just make sure that you remember that the counters changed as well. So y starts at n equals 0, y prime starts at n equals 1, and y double prime starts at n equals 2. Okay. Let's go ahead and see what the process is for using a power series to solve a first-order differential equation. The process is long, and it's super tedious. And the best way for us to see how to do it is to actually work through an example, but I have written up a summary of all of the steps. Some of them may not be clear to you until we actually reach that point in the problem. So the first thing we're going to do is we're going to substitute series forms in for y prime, and in the next section we'll do y double prime as well. Next, we're going to shift indices so that all the series have the same x to the n in them. Then we'll add out any terms needed to make all the counters start at the same time. Next, we combine the series by adding or subtracting, and we come up with a general form for the coefficients of the terms of the series. And then we equate coefficients given that you have an infinite sum of polynomial terms on the left side and a zero on the right side of an equation. And once we have enough coefficients, we form the solutions by listing the first several terms of the series solutions. Now, WebAssign has some problems that ask for a Maclaurin series or Taylor series representation of the solution. You just use the table that's provided in the textbook to help you. In class, I'm not going to ask you for that. I don't care if you can come up with the series representation. I just care that you know this process and you can list the first few terms. I don't want it to feel like a trick and you have to figure out a Taylor series. All right, so let's start with an example. We want to find a power series solution of y prime minus 2xy equals 0. So first, we're going to substitute, First, we're going to sub y equals the sum n equals 0 to infinity of c sub n x to the n, and y prime equals the sum n equals 1 to infinity of c sub n x to the n minus 1 into the differential equation. So when we do that, we have the sum n equals 1 to infinity of c sub n x to the n minus 1. I'm going to write my n's a little bit more clearly. Minus 2x times the sum n equals 0 to infinity of c sub n x to the n equals 0. So I just replaced y prime and y with their power series representations. The next thing I want to do is distribute the 2x, because I can't have that hanging out outside of my summation. I can have a sign on the outside, but I don't want any constants or any x's hanging out on the inside or outside. So when I distribute them, I end up with the sum n is 1 to infinity c sub n x to the n minus 1 minus the sum n goes from 0 to infinity of 2 c sub n. That x will combine with the x to the n so that I have x to the n plus 1. And the sum is equal to 0. All right, the next step is to shift the indices. Okay, so in the first series, it looks like in the sequence I need to add 1 so that I can get an x to the n, which means in the counter I subtract 1. In the second series, I want x to the n, so I need to subtract 1 everywhere there's an n, and to balance that, in the counter I need to add 1. And so I do that. I get the sum, n goes from 0 to infinity since I subtracted in the counter. Now I'm going to add 1 everywhere I see an n in the sequence. So I get c sub n plus 1 times in parentheses n plus 1 and x to the n minus the second one. And the second one I'm adding in the counter, so it becomes n is 1 to infinity. And everywhere there's an n in the sequence, I subtract a 1. So I get 2 c sub n minus 1 x to the n. And this all sums to 0. Okay, so I shifted my indices. And then the next thing I want to do is add out any terms to make the counter start in the same place. So we're going to add out, and it looks like I need to add out the n equals 0 term in the first series. Then they'll both start at 1. So the n equals 0 term will be c sub 0 plus 1 times 0 plus 1 times x to the 0. Plus, now the counter can start at 1 and go to infinity. C sub n plus 1 times n plus 1, x to the n, minus the sum, n equals 1 to infinity of 2 c sub n minus 1, x to the n equals 0. All right, now I can go ahead and combine the series. So that one term is still just going to hang out. It's C1 plus, now factor out the common sum, n equals 1 to infinity. That leaves behind my coefficients. So I'm going to factor out my sigma notation on the left and my x to the n on the right. So my coefficients are c sub n plus 1 times n plus 1 minus 2 c sub n minus 1, close the parentheses, times x to the n equals 0. Okay. Now, what I get from this, on the left-hand side, I have a polynomial. On the right-hand side, I have a polynomial, although it doesn't look like it because it's a 0. But you could think of the right-hand side as having a plus 0x plus a 0x squared plus a 0x cubed, and so on and so forth. And so we want to equate the coefficients with what we've got on the left-hand side. So we need to come up with a general form for the coefficients. And we do that by, number one, I look at this first term, C1. C1 stands alone. And on the right-hand side of the equation, I have zeros. I'm saying that C1 plus a whole bunch of sums is adding up to 0, then C1 is 0. And the coefficient of the x to the n's is 0. So the c sub n plus 1 times n plus 1 minus 2 c sub n minus 1 has to equal 0. So that's what I get from equating coefficients there. It gives me my general form. So C1 is 0 regardless, and then in this general form here, I can solve for the later index in terms of the prior index. So what that means, n plus 1 is a bigger number, so c sub n plus 1 is what I'm solving for in terms of c sub n minus 1. So it will be 2 c sub n minus 1 over n plus 1. And then we have the C1 is equal to 0. What we don't have any information about, like it's missing, is there's an implied C naught equals C naught. There was no information given about it, but I need to assume that C naught is part of this whole game here, because our solution should be y of x equals C naught plus C1x plus C2x squared plus C3x cubed, and so on and so forth. So C naught's got to be there. When it doesn't show up in the equating coefficients part, we assume that it is itself. Like I could call it, K or whatever, but I'm just going to let it be C naught, so it's not confusing at all. Okay, next, what I'm going to do is I need to come up with several of the coefficients. So we're going to come up with several of the coefficients. Oftentimes in the homework and on quizzes and on exams, I'm asking for 4 or 5 terms. And so that's several. All right, so what I do is I make a table where one column is values of n, And one column is this general form, c sub n plus 1 equals 2c sub n minus 1 over n plus 1. Okay. If n is 0, then what I get is c sub 0 plus 1, that's c1. And we already know c1 is 0. Okay, so when n is 0, we already know c1 is 0. That's a given. Okay. But when n is 1, we get new information. Plugging in 1 for n in the general form, I get c2 is 2c0 over 2, which is just c0. And c0 is just c0. Like it's just some number. It could be any number, actually. We'll leave it c0. Then I can go to 2. N is 2. Then I'm finding c3, which is equal to 2c2 over 3. But this is, hang on, not c2. c1. 2c1 over 3. But c1 is 0, so this is just 2/3 times 0, which is 0. So I don't get anything for c3. When n is 3, I get c4. c4 is 2c2 over 4, which reduces to 1/2 c2, which is c0. And I leave it like that because c0 is just c0. When n is 4, I get c5, which is going to be 2c3 over 5. But c3 is 0, so this is 0. I'll get one more. When n is 5, c6 is, plugging in 5, I get 2c4 over 6, which is 1/3 times c4, which is 1/2 c0. So that simplifies to 1/6 c0. Okay, now let's see what we're going to do with this. Our solution is y of x equals the sum, n equals 0 to infinity, of c sub n x to the n. That's how we started this whole game. We said let y of x equal this. Let's write this out. When n is 0, I get c0. When n is 1, I get c1x. When n is 2, I get c2x squared, and so on. I keep going. I'm going to go up to c6, where I get plus c sub 6 x to the, whoops, my c sub 5 went with x to the 5th. C sub 6 goes with x to the 6th, and then this goes on in this manner forever. The reason why I wrote this out is so that we go back to like, what were we doing anyway? Because oftentimes this is where people get stuck. They're like, I found all these values and I don't know what to do with them. We go back to what our premise was. Y of x is a power series. And we just found the values for all the c's through c6. c0, we said, is just c0. So we'll go ahead and keep writing it as just c0. c1 was 0. So I get c0 plus 0x. Plus c2 is c0. So c0 x squared. Plus c3, well, c3 is just 0. So 0x cubed. Plus c4, which is 1/2 c0 x to the 4th. c5 is 0, so I get plus 0x to the 5th. And finally, c6 is 1/6 c0, and then times x to the 6th, and so on and so forth. Okay, now I can simplify this and make it look a whole lot better if I don't write those 0 terms, right? We can make those go away in our expression, but I'm also going to factor out a c0 since it's common to everything. So we get c0 times 1 plus x squared plus 1/2 x to the 4th plus 1/6 x to the 6th, and so on forever. This is our general solution for the differential equation in a power series form. Okay? Now, it turns out that the problem that we were working with could actually be solved as a separable equation, but the solution that we get, whatever it is, can be represented by this power series. So that's the thing to go back to as well, is that in Calculus 2, we learned that many of the functions that we work with can be expressed as an infinite power series. And so we're just finding the infinite power series solutions to differential equations that we've worked with. As always, if you have any questions at all while you're doing the homework, please feel free to reach out.